So, this is where we got to on Wednesday. We talked about feedback loops, and we introduced this horribly confusing notation that hopefully you're getting to grips with now a bit. And we ran out of time a little bit at the end, so I just wanted to make sure that we knew what we were doing. So here's my example of a positive or an amplifying feedback. And remember, positive isn't a good thing necessarily. In fact, when this feedback gets going, it's generally a bad thing for our climate because it means it's destabilizing. It's pushing it further along once we have an initial change. So as an example, if we decrease the temperature of our planet, we can increase the amount of ice. If we're increasing the amount of ice, we're going to increase the amount of incoming sunlight that we reflect straight back to space without it actually warming us up. And so if we're increasing the amount of sunlight we reflect back, then we're also going to continue to decrease the temperature of the planet. So according to this feedback loop, once we start decreasing the temperature of the planet, it just gets colder and colder and colder and colder and colder. And that's what I said has actually happened. This is something that we think happened in the past, maybe about 700 million years ago, a couple of times. This feedback kicked in because the continents were in a slightly different position. And we did become almost entirely covered by ice and snow. It was a really very miserable time. And the question that I didn't get to ask at the end was, well, why are we still not a frozen ball of ice and snow? If I said that there's this positive feedback and it just keeps getting colder and colder, what else, other than things like reflecting sunlight out to space, what else might change on Earth that might mean that we're not trapped forever as a ball of ice and snow? Yeah. Increase carbon dioxide, absolutely, which is of course what we're doing today. So we can increase carbon dioxide. Does anyone know where carbon dioxide comes from other than we're putting it into the atmosphere by burning it? Someone muttered it, I think, over here. Volcanoes, absolutely. Volcanoes put out lots of CO2. When they explode, it's because there's lots of gas. So they put out water vapor, but they also put out lots of CO2. And that's really what saved us, because volcanoes don't care if we're covered with ice and snow. The volcanic activity kept going while all of the Earth was covered. And so what happened was we built up enough CO2 in our atmosphere that we warmed it, and then we started melting our ice. And then we followed that feedback, but we went the other way. We sort of went in the other direction. Okay? And so that was what saved us. And that was a nice introduction, I thought, to today, because we're going to talk about all of those different things that control our planetary temperature. It isn't just a matter of energy from the sun and being reflected back to space. We also need to think about things like the composition of our atmosphere, what's happening to that energy. So today, what we're really going to focus on is energy. What is energy? Are there certain laws that we can use to predict how it will behave? And we're also going to look at the sort of 5 factors there that control our surface temperature, that keep us at the nice temperature that we're at right now and has allowed life to remain on Earth for so long. So first of all, what is energy? It's something that is a word we use, but we don't necessarily often define it. And it's the ability to do work or to move matter. And so that's all very well, but what is work? It's sort of lifting anything, pushing or pulling anything. Doing just about anything is work, and that requires energy. And we have 2 particular types, 2 categories of energy. We have kinetic energy, which is to do with movement. That can be the movement of electrons if you're talking about electrical energy. It could be the movement of atoms vibrating as you get warmer, as you put heat in something. That's thermal energy. Or it can be potential energy. So potential energy is, for example, that stuff that's stored in your Mars bar, the chemical energy that you then gain and can burn to obtain energy. That's potential energy. It's locked away in sort of compounds until you use it. But also things like gravitational potential energy. So if you're really high up, you've stored up a lot of potential energy, which then you can convert as you sort of go down. And energy is often measured in calories, or what we're going to use is joules. Okay, 1 calorie equals 4 joules. So, hopefully everyone is familiar with this thing, even if I won't go on them. I'm sure you guys will. So, where would I have the greatest potential energy on here? The top, absolutely. Where would I have the greatest kinetic energy on here? The bottom, okay. And that's really what you've just described to me, the first fundamental law of thermodynamics, which is that we can convert that potential energy when you're just at the top there. Okay, you have a lot of stored potential energy, and as you move downwards, you're converting that potential energy into kinetic energy. So that's our first law there, which is in a system of constant mass, the energy involved in any physical or chemical change is neither created or destroyed. It's just changed from one form to another. Okay, and that's really as sort of complicated as we're going to get. We can have potential energy converted to kinetic. What happens as you go up the other side is you're then converting that kinetic energy again into potential energy when you get to the top. Okay, so my second question is, if I had another identical loop right next to this one, if it's not powered, if it just rolls off the top, will I make it necessarily all the way to the top of the next loop? No. And why not? We said, well, we have to conserve all that energy. It's because of that second law, which says that energy changes from a more useful, more concentrated form to a less useful, less concentrated form. So we're not changing all of that potential energy into kinetic movement of just that sort of roller coaster. What we hear it, so there's sort of vibrations in the air, so that's where some of the energy is going. It's going into friction, that heat energy. So it's not completely efficient just converting one to another, because we also create these other forms of energy that we then can't use, less useful forms. Okay, so that's a very, very brief introduction to the laws of thermodynamics. So now let's talk about power, because that's more what we're familiar with, because wattage is your average light bulb? 100 watts, well that's a really bright light bulb. If you go to IKEA now, it's more like maybe 15, 20. They've got really much more efficient about it. But yeah, you can have it's somewhere between, say, 15, 100, something like that. And that is to do with power. Power is how quickly energy is used. So when we talk about a watt, what we mean is that it was burning this many joules per second. Okay? So 100 watts is 100 joules per second. So that's our light bulb. Let's look at the sun. The sun produces 3.865 times 10 to the 26 watts, which is this many watts. It's a little bit brighter than your average light bulb. And you can tell, because if you go outside on a hot day, you can feel that heat, even as far away as we are. It's enormously powerful. It's producing enormous amounts of energy. And of course, we don't get all of that energy, and we'll talk about that in a while. But the sun is an amazing source of this power. And the power that comes out of the sun, the energy that arrives at us or to us from the sun, is in the form of electromagnetic energy. And really, it's called electromagnetic energy because what it is an electric field and a magnetic field that sort of travel perpendicular to each other, or at perpendicular sort of angles towards us. Okay? And you've heard of it, but you've often heard of lots of different categories. So things like visible light is electromagnetic radiation. X-rays, radio waves, gamma rays, ultraviolet radiation. These are all forms of electromagnetic energy. And each of those categories has a specific range of wavelengths, but they all travel at the speed of light. Okay, and that speed of light is about 300,000 kilometers a second. And we're going to use a couple of different terms today. Mainly, we're going to use wavelength. And wavelength is really just saying, well, if I look at the top of that wave, how far is it to the top of the next wave? That's our wavelength. So you can see that my waves on the left-hand side here are longer wavelengths than my waves on the right-hand side, which are closer together. Those peaks are closer together. Okay? And so higher energy waves have shorter wavelengths. Higher energy waves have shorter wavelengths. And to do with that wavelength, we therefore see a change in the frequency. So frequency is how many crests pass a given point in each second. So you can imagine that if I had like a little wall here and this was traveling towards it at the speed of light, I would only see a sort of peak every now and again compared to over here, and I'd see many more peaks hitting that line as it moves forward. So higher energy waves also have higher frequencies. So shorter wavelength equals higher frequency. Okay? So here's our electromagnetic energy, and it's a spectrum. It doesn't all come in one particular wavelength. It comes at a whole range of wavelengths. And we've somewhat arbitrarily just sort of created points where we say, well, we're going to call anything with this wavelength gamma radiation. We're going to call that, say, visible there is the wavelength from 0.4 to 0.7 micrometers, so millionths of a millimeter. Okay? And so those are the different categories. And we're going to come back to why this is important in a second. So what emits energy? Basically, you'll be emitting energy. Anything that is above absolute zero, anything that has sort of thermal energy will emit energy. And so I want to introduce you to the Kelvin scale of temperature. Has anyone not heard of the Kelvin scale before? Good. Most people have. The Kelvin scale is a much more sensible scale because absolute zero, the point at which things don't have any energy anymore and don't vibrate, is 0. We use, in Europe at least, the Celsius scale, and in science we use the Celsius scale. And with the Celsius scale, 0 is where water freezes, and 100 is where it boils. The Fahrenheit scale is, I don't understand it. I think it's crazy why you guys use it. But it's 32 and 100 and 212 or something. We're not really going to use that. Sometimes I'll be nice and I'll give you an idea of what the Fahrenheit is when we're talking about big changes in temperature on Earth. But really, we want to use Celsius because we're scientists. And in particular, if we're using physics, then we have to use this Kelvin. And so when we see temperature in the remaining equations today, we're going to be using temperature in Kelvin. And it's a really simple scale because 1 Kelvin is equal to 1 Celsius. So if we're at 0 Kelvin, we're at minus 273 Celsius. If we're at 1 Kelvin, we'll be at minus 272 Celsius. So it's pretty easy to convert between those. So the sun emits a spectrum of radiation. And when I say a spectrum, I mean this sort of range of wavelengths. It doesn't just emit radiation at one particular wavelength and that's it. It emits that whole range. It emits some ultraviolet light, it emits some visible light, it emits some infrared, all of those different categories that we were looking at. But it does have a peak wavelength that it likes to emit, and that is actually in the visible range. It's that nice yellow that we see. Okay? So you can see that our solar spectrum, what we would measure at different wavelengths, outside our atmosphere at least, is marked in the orange color there, or the red color. And blue is sort of the theoretical spectrum that would be emitted by a black body. And what do I mean when I say black body? It's this idea that physicists came up with. And a black body is anything that absorbs all of the light shined upon it, and it emits a spectrum of light that depends on its temperature. Okay? And it is, in reality, hypothetical. But for our purposes, it's close enough, or the sun is close enough to this black body that we can use these laws that sort of govern a black body behavior to make predictions about the amount of energy and also what wavelengths of energy the sun will give out and other bodies will give out too. So for some reason, that first equation always gets offset in my notes. But these are the equations that we're going to use. And don't look terrified quite yet, because they're really very simple equations. The first one is the Stefan-Boltzmann law. And what this law basically says is that the hotter you are, the more radiation you're going to give out, which I don't think is a surprise to anyone, because you've all had sort of barbecue at the beach or whatever else, and you know that the hotter the coal, the more energy it gives out, the more heat that you feel coming out of it. And so that I is just radiation in watts per meter squared, so how much power is coming per unit area. And then it's equal to just the Stefan-Boltzmann constant, and then times the temperature in Kelvin to the power 4. And what that power 4 tells you is that even if you raise temperature just a little bit, you're going to really much more greatly increase the amount of power or amount of radiation that that gives out. Okay? So hopefully that one makes sense. And the second that we're going to look at is Wien's law. And Vine's law says that that maximum, that peak of that nice sort of spectrum, that peak wavelength of the emission is equal to 2,898 divided by the temperature, again in Kelvin. So now what happens to our wavelength as we increase temperature? Does it increase or decrease? Yeah, it decreases. As we're increasing T, we're dividing by it, so we're going to decrease our wavelength. So the warmer something is, the shorter the wavelength it emits. Okay? So we can also look at that much more simply, I think, in a graph form. And my graph on here has increasing flux, so basically increasing energy emitted on the y-axis, and then wavelength from short to longer along the bottom. And we've got 5 different curves on here, and those 5 different curves are emitted by things with different temperatures. And the Stefan-Boltzmann law says that that total energy is a constant times temperature to the 4. And the total energy is basically the area under the curve. And then Vine's law says that that wavelength of maximum emission, that peak on my spectrum, the peak point, is going to be a constant divided by temperature. Okay, so you can see that each of those 5 different curves has a different peak. So tell me, looking at those laws, looking at what I've put on there, which of those curves is emitted by the second hottest body? Okay, I think we're missing a few more people today, so if anyone hasn't answered, if you want to put your vote in. Right, let's take a look. Great. So I think most people have that. So B would be the correct answer, because if we're looking for the area under the curve, if we say just look at A, which would be emitted by the hottest one, then the A curve has the greatest area underneath that line. And so it's giving out the most energy. So our second hottest will be B, because it's that second greatest amount of energy, second greatest area under the line. And you can also see that Vine's law is also telling us the same thing. It's saying that as we increase temperature, remember, we're decreasing our wavelength. And that's true, because our coldest line is E, and it's got the longest peak wavelength. And then as we get warmer and warmer and warmer towards A, our peak wavelength shifts, it gets shorter. Okay, so hopefully that makes sense. If you have a look over it again, I think it will make sense to most people. And that's just a little summary. Okay, and I think the really neat thing about this is that you see this, because everyone has hopefully been to a barbecue or been down to and had a bonfire at the beach. And what color are the very hottest coals? Do they sort of glow reddish, or do they glow white? White. They're white hot. Absolutely. So they're sort of closer, or they sort of encompass more of these colors, and so they give out this white color. But as they cool down, they start glowing sort of yellow, and then they start glowing red. And then after that, they're still giving out energy. You can still feel that heat, that energy coming off, but they're not giving out visible anymore. They've cooled enough that they're now giving out this longer wavelength that our eyes aren't adjusted to see. And it's actually infrared. That's what it's giving out. So you're familiar with this idea. You've all seen it in action. We're just putting sort of some science terms to that. And why is this important? Why am I going on and on about this? Well, it's going to become very important when we talk about the greenhouse effect, because the sun is so hot. If we put the temperature of the sun, which is 6,000 Kelvin, into our Vine's law, then we get a peak emission for the sun in the wavelength range of about 0.48 micrometers, which is, remember, a millionth of a meter. And we call that short wave radiation. If we then put the temperature of the Earth into our Wien's law equation, which is about 300 Kelvin, then what we get out is something much more like 9.66 micrometers. And we call that longer wavelength. It's in the infrared range of the spectrum. Okay? So we have short-wave radiation coming from the sun, long-wave radiation coming from the Earth. So that's going to be important later. So now let's look at these factors that control Earth's temperature. So first of all is the sun. That's where our source of energy is coming from. And so we really care about the luminosity, that power that's coming from the sun. And in general, over billions of years since the sun first formed, it's been getting brighter. And that's completely reversed to as what we usually think, right? We usually think that sort of things are bright to begin with and they sort of die off. But actually the sun is getting brighter. And it's expanding. It might end up swallowing the Earth someday in 5 billion years' time, so don't worry about it. But over that, so billions of years, it's been getting ever so brighter. On a short time scale, we also see little variations in solar output. We have what we call the sunspot cycle. And we haven't really had very many recently, so you might not have heard of this so much. But the idea is that on an 11-year cycle, we get more sunspots, which is equal to more energy coming from the sun, and then we get less sunspots and less energy. And we have quite a good record of sunspots because people in Europe liked counting them in the 16th and 17th century. And we can see that not only do we have an 11-year cycle, but we also have some sort of natural, longer range variability as well. And to be honest, we don't really know how to explain that terribly well. The sun is an amazing thing, but it's really complicated. It's difficult to measure, and so we still don't understand quite a lot about the fundamental physics of the sun, and it's a really fun idea. So we definitely care about the sun and how much energy it's giving out, but really on our sort of timescales, it's not changing very much. The other thing that we need to think about is obviously our distance from the sun. If we're closer to the sun, we're going to get more of that energy, and so we're going to be warmer. And really, this doesn't fundamentally change through time. I do want to stress we're not moving further or away from the sun. But these two factors combine to create something that we call the solar constant, or it's also sometimes called the solar flux density. And it sounds really complicated, and again, it isn't. This is the idea. So here's our sun. The orbit of the Earth is marked in that sort of purple circle there, and the orbit of Mars is marked in the green. And what this basically says is that if I have a light bulb, and I put that light bulb in a little cardboard box at the front here, then on the inside, each little area of that cardboard box is going to be really brightly lit. If I have that one light bulb, and I rely on it to fill this whole room, then each little area of the wall is actually going to be more dimly lit. It's going to receive less of that energy. And it's not because the energy is sort of dying off or anything and not quite reaching the wall. It's just, it's spreading out. And as that energy spreads out, we're getting less per unit area. Does that make sense? Yeah, hopefully. And so all we have done is create a little formula that tells us that. So we're saying that the total amount of energy that the sun gives out is that luminosity, that 3.865 times 10 to the 26 watts. But in reality, that's not all coming our way. It's spreading out in all directions. And if we want to know how much per meter squared the Earth actually receives, then what we can do is use that distance from the sun to draw a sort of a sphere around the sun and work out how much per little meter squared we get. So our solar flux density is equal to the luminosity divided by the area of the sphere that's created using the radius of Earth's distance from the sun. And if we do that calculation, we get something like 1,367 watts per meter squared. That's how much energy we receive at the top of Earth's atmosphere from the sun. Okay? So prove to me that you've been following what I've been saying. So is the solar constant of Mars, is it going to be greater than the Earth? Is it going to be less than the Earth's, or the same as the Earth's? So think about it for a second, consult your neighbour, and then when you've thought about it, let me know what you think. So I think we've got most votes again. So if you want to register your vote, and we'll take a look at the answers. So most people said B, less than the Earth, and they would be right. Well done, guys. And why is that? So for those of you that weren't quite so certain, the Mars is further away from the Sun than the Earth, and so its radius, so the distance from the Sun to Mars, is greater than the Earth's. So our area of the sphere is greater, and if we're dividing the same luminosity by a bigger number, then we're going to decrease our solar flux density. Great. So that's all very well. I said, well, that's how much energy we're getting per meter square at the top of our atmosphere. And why did I say the top of our atmosphere? Because weird stuff happens to it. It has to try and travel through the atmosphere to get to us down here at sea level. And so let's look at what actually happens to that energy. So here's our solar spectrum outside the atmosphere again in that red line that we saw earlier. But there, sort of filled in, is actually what we'd measure if we went outside here and sort of looked at that solar spectrum. And so you can see that, first of all, we just get a lot less than what the top of the atmosphere seems to receive. And also what we seem to see is really weird sort of blips where we're actually not receiving any energy in those particular wavelengths. And again, this is actually going to be related to the greenhouse effect, because visible light can come more or less straight through the atmosphere, but actually certain gases in our atmosphere like absorbing energy at those particular wavelengths, and that's why we don't see them coming in either, and that's why they also can't escape. So we know that weird things are happening. So what's actually happening? Well, first of all, a certain amount of that incoming radiation is just reflected straight back to space. We've already got used to that idea because we talked about ice and snow being so reflective. But remember, we've also got lovely, nice, white, fluffy clouds around a lot of the Earth, and so they reflect back a lot of that incoming radiation. We also have something we call scattering, and that's something that, if you look in a beautiful mirror, it just reflects your image back at you. If you look at something that isn't quite so polished, then you might see sort of a blurry image. That's more scattering. It's not sort of in, out. It's more sort of scattering it and deflecting that light in all directions. And some of that scattered light ends up going back to space. It's also why the sky is blue, by the way. If anyone wants to know more, then let me know. And then the rest of it is actually absorbed by the Earth. So we reflect very little by the ground. A lot more of it's reflected by clouds. But about 70% of it is either absorbed by the atmosphere or absorbed by Earth's surface. And that goes into warming us up. Okay? So I keep talking about this idea that we reflect away a certain amount, and we actually have a term for this. And the term is called albedo. It's a really funny word, but we say that our planetary albedo today is 30%, or you can call it 0.3 if you prefer, and that's the percentage of incoming solar radiation that just bounces straight back to space. Okay, so that's the word that we use for that, and that's the word that you'll often see in those feedback loops from now on. So my question for you is, can you think of ways in which the Earth's albedo might change on short and long timescales? What do you think might have happened in the last week or so to Earth's albedo, perhaps in the northern hemisphere? Yeah, there was more snow and ice. If you saw those satellite photos of North America, it was really white, right? And so, yeah, we reflected back more of that incoming solar radiation. And that's a very short time scale, because next week a lot of that ice and snow might be gone. What else could we do to change Earth's albedo? So perhaps not greenhouse gases. That matters more for when we're trying to emit energy out to Earth in a second. What else did we say was nice and white and reflective? Clouds and ice, definitely. So clouds are a good way. So some days it's clearer than others. So definitely the amount of clouds on Earth can affect our albedo. And this is actually one of the things that we're somewhat uncertain about going into the future. Clouds are something that are really difficult to get right in our climate models. And so a lot of our uncertainty in predicting some of the future climate change is to do with things like how much extra light might be reflected back from clouds compared to how much they might absorb. And on long time scales, what do you think might happen? If we went back 20,000 years ago, what would we find over a lot of North America and Europe? Big ice sheets. We were in our ice age, and so obviously at that point as well, we had a lot more albedo. We were reflecting more light out to space. But also things like changing sea level, changing the forests. We have deserts compared to grassland. All of these different surfaces reflect back slightly different amounts of energy. And so this is my challenging evil eye clicker question of the day. So I'm going to give you a couple of minutes to think about this one properly. So which of those below changes, A, B, C, or D, would decrease Earth's albedo, so decrease the amount of energy reflected out to space, and so would increase temperature? And this table here gives you a lot of different surfaces and the albedo for each of those surfaces. Okay? So have a think, consult your neighbor, and I'm going to give you a couple of minutes before I ask the question this time around. So which of those would decrease albedo? And the TAs are around as well, so consult your TA. So I think most people have made their decisions, so if you haven't, then add in your best guess. Okay, let's take a look and see if, as a class, we have a winner. My goodness, guys, you're brilliant. Well done. Okay. So well done. For those people that aren't quite so certain, and just in case you forget it all, if we increase snow cover, we're going to increase our albedo because it's much more reflective. We're going to reflect more out to space. The same thing happens if we increase our cloud cover. We're going to reflect more out to space. We're going to increase our albedo. If we look at, say, forests actually are pretty good at absorbing a lot of energy, and that makes sense because they're designed to. They want to take in that energy because they use it for photosynthesis. Whereas deserts actually reflect back a lot of that incoming energy. And so if we replace our nice absorbing forests with more reflective deserts, we're also going to be increasing our albedo. Whereas water, the ocean, is really good at absorbing energy. Very, very good. It has sort of the lowest albedo, really. And so if we're increasing sea level, we're flooding areas of continent, perhaps. And really, whatever we're flooding is going to be more reflective than that ocean. And so our ocean is going to increase in sea level or decrease it. Well done, guys. I'm really impressed. Thank you. So I said that we're reflecting back that certain amount and scattering away a certain amount. But we're also absorbing 70%, which is actually a lot of energy, right? And so why doesn't the Earth get hotter and hotter and hotter and hotter and boil off our oceans and sort of disintegrate? It's because of that thing that we said before, which is anything with a temperature, anything above absolute zero, also emits energy. And so because the Earth also has a temperature, it will emit energy. Okay, so Earth's temperature is also a factor that controls Earth's temperature. So feedback. And the idea is that we reach an energy balance. So what comes in from the sun, what we absorb from the sun, is equal to the amount of energy that we emit. Okay, and the amount of energy that we emit is again related to that Stefan-Boltzmann law that we looked at earlier. That sort of energy radiated equals that Stefan-Boltzmann constant times by the temperature of Earth to the power 4. So if we increase the amount of energy we absorb, we're going to increase our temperature, but that will therefore also increase the amount we emit. So we always find this balance, and that balance means that we're, at least on an annual average over the whole Earth, in balance. Okay, so remember I said that this was going to come back to us. The fact that the sun is much, much hotter than Earth, which is a good thing. And that means that, according to Wien's law, according to those black body laws, it emits shorter wavelength radiation. And in particular, it emits visible radiation compared to the Earth, which emits long-wave radiation or infrared. And that's important for our greenhouse effect. And most people have heard about the greenhouse effect, but they might not have heard about it for a while. So this is a horrible-looking graph. And everyone always tries to ignore this and just read the writing. But this graph is a really nice demonstration. If you can put a couple of minutes into understanding this, I think it really helps. So all of these different colors here represent different gases. So at the top we have methane. then nitrous oxide, oxygen and ozone, carbon dioxide, water vapor, and then at the bottom in purple we have the whole atmosphere, so the composition of the whole atmosphere. And at the bottom here we have a wavelength, and in this case we've reversed it, so the shortest wavelength is now at that end, and the longer wavelengths are at this end. And wherever you see colour there, that's where that gas is best at absorbing that wavelength. So for example, if we look at, say, methane at the top there, it's really good at absorbing energy at this particular wavelength and at this particular wavelength. And you can see, for example, water vapor, it's not something we talk about very often, but water vapor is actually by far the most powerful greenhouse gas. It absorbs by far the most of that infrared energy compared to carbon dioxide. The difference is that we want water vapor in our atmosphere because we want it to rain and we need precipitation, whereas things like carbon dioxide we definitely don't necessarily need as much of in our atmosphere. So if we add up all of those different columns, you can see that this thing is really in the way. Hang on, let me see if I can move it. This range here, you can see it says UV up there, it's ultraviolet. And which gas do we know is very nice for us because it helps absorb incoming ultraviolet radiation? There's a hole in it, unfortunately. Ozone. You can see oxygen and ozone, and you can see that in that column, it absorbs nearly 100% of this really nasty, damaging, high-energy shortwave radiation. That's why it's such a good thing for us on Earth. Then if we look at visible, so you can see there's a visible range there, we mark that down, there's really very little in our atmosphere that interacts with those particular wavelengths. And that means that those visible wavelengths coming in, unless they're reflected back, they come straight through the atmosphere, just like light coming straight through a window. Okay? But remember we said that the Earth then absorbs that energy, and because it's a lower temperature, it emits, instead of visible light, it emits infrared radiation, that longer wave radiation. And this is why we're in trouble, because now these are our infrared wavelengths. And look how good the atmosphere is and those different gases are at absorbing energy in those particular wavelengths. So we have our nice visible shortwave radiation coming from the sun that comes straight through and hits the ground and we absorb it. But when the Earth tries to radiate that energy back out to space, all of these gases get in the way and trap that energy. Does that make sense? Because that's a really important idea, I think. Yep. So we've got an explanation there. Okay? And so that energy that is trapped by those gases in the atmosphere then warm up the atmosphere. If we're adding energy, we're going to warm it up. And the key thing is that the atmosphere then emits energy again. Some of that energy goes straight out to space, and that's what creates our energy balance of the total energy absorbed equals the total energy emitted. It's the atmosphere that's emitting that out to space. But some of those gases in the atmosphere, it's emitting in all directions, so some of that energy will also come back down to the Earth. And so our surface is actually much warmer than it would otherwise be. Okay? So a more familiar analogy is, this is why your cars get really horrible and hot on sunny days out in the parking lot. It's behaving exactly the same way. Your windows act just like those greenhouse gases, because visible sort of nice shortwave radiation from the sun can come straight through your windows. They hit your lovely black seats and steering wheel. They heat it up. Your car is not as hot as the sun, and so it emits infrared radiation, that longer wavelength radiation, and that is trapped by your windows. It acts just like, those windows act just like those greenhouse gases, and so it keeps that interior much, much hotter than it otherwise would. Okay? So here's a little summary of what's going on. So we have incoming solar radiation, and you can see we have, ignore the numbers mainly on here, but there are two numbers that I want you to think about. We have 100 units of whatever the energy is on here coming in. We're reflecting back 30. We reflect 5 back from the ground and 25 from the clouds, the atmosphere up there. And then look, our outgoing infrared is 70. So our incoming of 100 equals our outgoing of 70 plus the 30 that's reflected. So whatever's coming in equals what's coming out. That's really our energy balance. But then you can see that more complicated things happen deep down, and that's because that energy is absorbed and radiated from the Earth's surface, but then that energy that's radiated in the long wave is being absorbed by the atmosphere. The atmosphere emits some out to space, but some also comes down. And so in general, we end up with a lot more energy circulating around at the bottom of our atmosphere. And that's really what our greenhouse effect and our energy balance is all about. So my last question for you is the greenhouse effect a bad thing? Very scientific sounding question, right? So is the greenhouse effect a bad thing? Okay, a few more seconds. So don't pack up just yet. I have 2 more important things to say. So let's take a look, see what we have decided about. So C, we'll say sometimes, and I think the clue is in the question, absolutely. So the main thing I wanted to get across with this question is that people have mixed up the greenhouse effect with climate change. And actually the Earth, in order to keep it a nice, comfortable temperature, we need the greenhouse effect. If we had no greenhouse effect, the average temperature of Earth, not at the poles, the average temperature would be 0 Fahrenheit or minus 18 degrees Celsius. And that's not really livable. It's not really usable for plants and people. And so with our greenhouse effect, we actually, and a lot of that is water vapor, we have a lovely, nice, comfortable 60 degrees Fahrenheit, plus 15 degrees Celsius. The complication arises is because we are strengthening the greenhouse effect. The additional CO2 that we're putting into the atmosphere is strengthening that greenhouse effect. So in general, it's not a bad thing that we have it. We need it to be able to function. But that additional greenhouse effect, that is what climate change is all about, that little bit extra. Okay, great. So on Monday, we'll look at Earth's climates.